Okay, I think we'll get started. So today we are continuing with kinetics and trying to figure out the rate law. And so we're going to talk about integrated rate laws today. And so what we're going to do is go through the common orders, 0th order, 1st order, 2nd order, which are the typical ones you will see in your general chemistry book as you practice this. And what we'll do is we'll develop the way to take a Excel spreadsheet of time versus concentration data, and by plotting those data, figure out what the order of the reaction is. All right, so I think what we'll do is we'll start with 1st order, then we'll do 0th order, and then we'll do 2nd order. So a 1st order reaction, we have V equals Ka, let's say, for a reaction A goes to products. The elementary reaction, A goes to products. Now, this doesn't have to be elementary. If we, in fact, here in this procedure, we're going to be plotting data and figuring out what the order is. So yeah, maybe I'll just leave it like this. Could be any reaction, and we'll figure out what the order is based on what those data look like. Well, what did we say V was? V for this case is minus dA dt, the rate of change, the instantaneous rate of change of A's concentration. The minus sign is that it's on the reactant side, and so it's disappearing over time. Now, we will be doing some calculus here, so if you've had some calculus, just follow along. It should be pretty easy calculus for you. And if you haven't, you can just either skip ahead and just pick up where we're talking about the results, or you can follow along and just sort of see what's going, knowing that you don't have to get it all down. So when we have this, we have something called a differential equation by putting V, which is this, equal to the power law here. And now we're going to use a technique of solution to this differential equation called separation of variables. And actually, if you're right in the middle of calculus now, we're going to do something that seems like something you shouldn't do. We're going to split apart these differentials, the dA and the dt, and we're going to get everything associated with A over to one side, everything associated with T over to the other side. And that's where the separation in separation of variables is coming from. Everything A on one side, everything T on the other side. So let's go ahead and do that. I'm going to bring up my dt over here, my A over here. I'm going to leave the K. I'm also going to just bring the minus sign. So with that, I have this like that. So this is just algebra, and we're treating the dA and the dt as just algebraic quantities, so we can split them and move them around. So now what we want to do is integrate this up to solve this differential equation. So the notation I like to use is I'm going to take this integral sign, and again, if you haven't had calculus, either just follow along and pop out the other side. If you've had some calculus, you'll know what an integral is. And so I use this symbol to represent I'm going to integrate both sides of this equation. So when we do that, we're going to get the integral and minus and k are constants, so I can pull those out of the integral. And I get this. This is the integral of 1 over x. So if you're just starting to learn your integrals, this is going to be natural log of a. Now, we should put plus a constant here. But in cases like this where we have an equation, we're going to get another constant over here. And so you could just as well take that, the constant that's coming out of this integral, the constant that's coming out of this integral, combine that as one constant. And that's what's done when you do this technique. So we don't put a plus constant over here. This integral is just t, but we definitely want a constant over here. Okay, let's now, what we need to do now is apply the initial conditions. So, A equals A naught, some kind of starting concentration when T equals T naught. Or when T equals 0. We'll just for convenience, we'll say we start the reaction at time equals 0. So let's go ahead and plug this in. We get log A naught equals 0 plus log a log C, sorry, plus C. So this means C is log A naught. So what I'm going to do is plug this back in here, but I'm going to write it up here under the linearized version here. So this is log of A equals minus kt plus log of A naught. And why is that under the linearized? Well, let's look at this. This is of the form y equals mx plus b. So it's the form of a straight line. And that will be important as we compare to the data that are collected. All right, so this is the linearized version of the integrated rate law. But let's go ahead and get the full integrated rate law by solving for A. So let me erase up here. And start with this. Now, how are we going to solve for A? We need to get A out of this log, so we exponentiate. So I'm going to use this same kind of notation here, E with the arrows, meaning we're going to exponentiate both sides of this equation. So when we do that, we get A, because exponentiating the log here, we'll just pull out the argument. And then we're going to have E to the minus kt plus log A naught. And now we're going to use property of exponents to write this as a product. And I'm going to switch the order here. I should put the A naught on this side. Well, this is just E to the log, so we have that. And so let's plot this. We get an exponential decay. So let's write this in here as our rate law. We have an exponential form for that rate law. Okay. Right, so that's first order. Let's go ahead and do 0th order. And so we just have velocity being a constant here. So we have minus dA dt equals k. There's our differential equation for this. So let's do our separation of variables. I'm going to bring the minus over. Now I'm going to integrate this up, and I'm going to get A equals minus kt plus c. All right. Let's get the initial conditions. So we get this equals A naught. And our final form, which is already linear, or which is still linear, is like this. So let me write this here. This is our final form. It's also the linearized form, so I'll just repeat that. So let's plot this. That looks like that. Just a little note here. Notice that if time just keeps going, we just go in a straight line and we end up having a negative concentration. And so what this says is that things can be 0th order only at the sort of the beginning of the reaction. Once we start to run out of reactants, of course the reaction has to stop if we don't have any of those reactants. So this will end up folding over and taking another form when the reactant is very depleted. But what we're usually interested in is in that early stage of that reaction. And so for a 0th order reaction, no reaction can be 0th order. And we see that because at the elementary level, there are no 0th order reactions. But reactions can be 0th order for a period of their reaction, but not fully through the whole reaction. All right, so that is 0th order. And let's finally do 2nd order. And we get this separation of variables again. So dt. So I'll do my integral coming through, and I integrate this side. I get a minus 1 over a. So raise the power by 1. And so that's a to the minus 1, and then divide by that power. Kt plus c. Okay. All right, let's apply the initial conditions. So let me do one more line before I pull it up to the linearized. Let's bring this minus sign over. So the equation that we're at now is that. And this is the linearized version. Okay, let me write that up here, and then we'll solve for A itself. And so that's just a matter of reciprocating both sides. I can, if I can leave it like this, or I can multiply through top and bottom by A naught. So I'll have A naught over A naught here. So numerator will be just A naught, and this will be A naught KT plus 1. Right, and if we plot that, that's going to look like kind of like a 1 over x. But at t equals 0, at t equals 0, plug in a 0 here, and A equals A naught. Okay. All right, so this is the integrated law. These are the integrated rate laws. And so how do we utilize them in practice here now, and how will you utilize them when you solve some of the problems in the book? Well, you'll be given a table of data, and the data are really just these two columns. And so these would be the raw data, and then these would be the process data. So what we would do here is simply take time. These can be any time unit, let's say milliseconds or seconds, whatever, and we're measuring the concentration. So that's a direct measurement of the concentration of the reactant as a function of time. So this should go down as the reaction goes. Then what we do in Excel is we make another column that is simply the log of the concentration. And then we make another column that is the inverse of the concentration. And so we have these four columns, time, and then the three other data columns. And then we will plot these columns as a function of time. I'm using Y here, capital Y, as a placeholder for each of these. Concentration, log, inverse. Okay, well, why do we do that? Because presuming the reaction is one of the three that we've talked about, and for all the data sets that you'll have in your book, whatever book you have, it will be one of those three. Then when we plot these data, one set will be linear, and two other sets will be curved. And so we match up the linear equation with the linear data set. So in this particular example, we plotted these, and it turned out that the red, which I'm representing here as the log, so this is the log of the concentration, is a straight line. And that means that this reaction is first order because the log is a straight line. Had the data itself been a straight line, then it would have been zeroth order. So if you plot everything and the blue would have been straight. Blue is the data itself. And then purple is representing 1 over. If that would have been straight, then it would have been a second order reaction. And so you can simply by linearizing these data, log and inverse, then you plot all three and you can pick out the order of the reaction. So I'm going to let you practice with that now, and I hope you can find some data sets in your book. Might be even easier to Google some maybe, or have ChatGPT make some for you, and then you can copy that and paste it into an Excel file and practice that way. All right, so one more thing we want to talk about is something called the half-life of a reaction. And let's again start with first order. So first order reaction, for example, is it's exponential decay. Second order is kind of like a 1 over. So you can't really characterize the length of a reaction or the time it takes for the reaction to go by waiting for it to go all the way to completion, because it comes to just a crawl as we get closer and closer to the equilibrium. So instead, a better characterization is to ask, how long does it take for the reactant to be at half of what it started with? And that's called the half-life. So let's do first order reaction first. So we use our integrated rate law. And then we will stick in so at the half-life, we're going to let t equals t subscript 1/2. So this is the particular time, it's one single value of time, when A equals A naught over 2. And so let's plug that in. A naught over 2 equals A naught e to the minus k t 1/2. And here's what's really interesting, and this is only going to happen for the first order reaction. The initial amount cancels. So a very special property of a first order reaction is that the half-life is independent on your starting amount, which is pretty interesting. So then we get 1/2 equals e to the minus k t 1/2. I'm going to go through and again use my notation here where I'm just going to log the whole equation. Now I'm going to use property of logs. Log of 1 over a is log of a, so is minus log of a. So this is going to become minus log 2 equals minus k t 1/2. The minuses can cancel, and then t 1/2 equals log 2 over k. And that's the half-life for a first order reaction. Let's go ahead and, I guess we could add that to this table. ln2 over k. We see with a bigger k, our half-life goes down inversely proportional to k, which makes sense. All right, well, let's do it for, you do it for second order, I guess. Let's actually start with the linearized version here. That might be easier. So again, t equals t 1/2, then a equals a naught over 1/2. So with the linearized version, we have A naught over 1/2 so let's bring this up here. That's 2 over A naught equals kt plus 1 over A naught. So let's bring this over to the other side. And so I'm going to have 2 over A naught minus 1 over A naught, which is just 1 over A naught. And this, oops, this should be the special time t1/2. And here we get t1/2 equals 1 over A naught k. And here we see that the starting amount matters. And this is interesting here. Well, let's do the 0th order first, and then I'll come back and talk about this. So there's our half-life there. And let's finish now with the 0th order. We'll have to, it strikes me that I might have forgotten to put the 2 here over here. Hopefully you caught that if that was the case. But at the half-life, this is 1 over 2. Certainly we did the result. This is the right result here. Okay, so for this one, let's use our equation. So and we'll plug in these. So bring this over to this side. Cancel the minus, bring the k over. Look how similar these look, but a very important difference. Both of them depend on the amount of starting material. In the 0th order case, the more you start with, the longer it takes to get to half-life because the reaction doesn't care how much you have. It's 0th order. So it just goes at a constant speed, and if we have to get rid of more of it to get to half, then it'll take longer. K in the bottom still, because this is determining how fast the reaction is happening. But here, the initial amount is actually in the denominator. So the more you start with, the faster you get to half. And that's because there's a strong quadratic dependence on the amount of material. So if we start with a lot, the reaction is way faster than if we start with a little. Okay, so this is integrated rate law. And it's something now you want to practice with. Maybe with a blank sheet of paper, see if you can derive the half-lives. Maybe as a challenge, you could see if you can get the integrated rate law for a 3rd order reaction or a 1/2 order reaction. If you've had some calculus, that would be some good practice for you. All right, so next we'll move on to talking about how the rate constant, although it's considered a constant in terms of the concentrations, it does depend on temperature. And we'll see that how temperature impacts the rate constant. We'll be talking about 2 theories for that, a simple empirical theory called the Arrhenius equation, and then one base that's kind of forcing some thermodynamics called the activated complex theory.